Thank you, Alyssa. Yes, it is my pleasure to be here to talk to you about water on exoplanets. So this is a completely different shift from what we had been talking about in the rest of the program. But in this talk, what I want to tell you about is my research is on this intersection between astronomy and geology. And I'm not going to focus on the actual role of water in biology. So I apologize if from my talk you were expecting a biology talk. This is not going to be one. What I'm going to talk about is the kinds of environments, the kinds of planets where we might actually find water to be stable on long time scales, suitable for complex life to develop on those planets. And so, as we know, on Earth, water is a fundamental component of biological systems, and it forms an important environment and an ecology where biology exists and can thrive. But what I want to talk about today is some of just a few actually, of water's many roles that it plays in overall planetary habitability on very long timescales. And what we've discovered in trying to find environments or planets where water is stable on long timescales is that water actually moderates the thermal evolution of a planet. The heat found within the interior of the planet is the driving energy that drives the geology at the surface of the planet. Heat causes the interior of the planet, the mantle, to convect. And on the Earth, that mantle convection is expressed at the surface as plate tectonics, which fundamentally alters and modifies the surface of our planet. And water actually plays a role in that thermal evolution process. And as a corollary, I'll tell you that water's presence on the surface, its continued presence over the history of the planet, actually depends on that plate tectonic process. And water on other planets can actually produce false biosignatures. In this case, these are planets that we might think would be habitable based on where we see them around a star, but in fact, they may actually have lost water, and the water may have produced a signature that we might interpret as signs of life if we're not careful in our interpretation. So here's an artist imagining of what the night sky looks like if you could zoom in with your telescope eyes on a patch of stars. What we have discovered, as Alyssa mentioned, in the last 25 years is that most stars, in fact, have planets around them. Here, the sizes of the planets are a little exaggerated so that you can see them, of course, but almost all stars have at least one planet. In this figure, we're showing a population of planets that has been discovered over the last 20 years. And in fact, this figure, I'll admit, is a little bit out of date, but it still shows you sort of the different kinds of populations of planets that we have discovered around other stars, many of which we don't have examples of in our own solar system. Here, the planets are the little points on this figure, and they're shown as a function of their size and radius relative to the Earth, and their orbital period in days. So the Earth would be out here at about 365 days on this line of 1. And so it falls in this population, this very large population of planets that we have discovered that we believe are rocky, potentially similar to the Earth and maybe Venus and Mars as well. Now, these planets have been discovered through two primary methods that gives us different information about the properties of those planets. The first is through transit observations, and in this method, what we're actually looking at is the planet's orbit is passing between us and the host star. And this is an image, an actual photograph of Venus passing in front of our sun that shows you exactly analogous what we're doing for exoplanets, is that we're looking for that shadow of that planet as it's passing in front of the star. And we're counting the light that we're getting from that star. And so the dip in light as the planet passes in front of it tells us about the size or the radius of that planet. The other method that we use to detect planets is called the radial velocity technique. And here we're measuring spectral lines from the star and looking at how those lines shift in wavelength due to the motion of the star about the common center of mass of the star and planet system. So here we're learning about the gravitational pull that the planet has on the star, and that tells us about the mass of the planet. And so these two methods combined tell us the mass and radius of the planet and tell us the density of that planet. And so when we have both measurements for a planet, we can confirm that it is in fact a planet and not some other astronomical event masquerading as a planet in our signals. Since the first exoplanet was discovered something like 25 years ago, we have confirmed 4,500 planets around other stars. And there's another more than 5,000 candidates for which we have maybe only one of these detections. And so it's not necessarily a confirmed planet, but we have up to almost 10,000 potential planets that have been detected around other stars. And amongst these 10,000 planets, we have discovered that planets, small planets, are in fact really common. Planets down here in this yellow range, where we might find habitable environments. Now, the planets that we want to talk about that have water on their surface that might be habitable, they exist in a region of space that we call the habitable zone. And the habitable zone is just an orbital range around a star at which on the surface of a rocky planet, water might actually be stable. And so this blue line, this blue curve that we're showing here is showing the position of the habitable zone for planets orbiting stars of different sizes. So the sun is up here at 1, but most stars, in fact, tend to be smaller than the sun. The most common kind of star is down here at lower mass ranges. And so we can see that the habitable zone depends on the mass of the star that the planet is orbiting. And it also changes with time as the star's luminosity evolves. Now, the boundaries of this habitable zone have been modeled based on predicted atmospheric properties for planets that would allow liquid water to be present on the surface of these planets. But something that's missing from this is actually the geology of the planet. So we know actually from looking at the Earth that water's presence on the surface over time, the abundance may change over time, and it depends on the operation of that plate tectonic cycle. So we know just by looking at the surface of our planet, we've heard a lot of great talks today about the effect that water has on our planet, the interaction that water has with our atmosphere, and the interaction that we have with it as human beings. But water also has a profound effect on the geology of our planet. So we can see this stunning image of this waterfall. The water is carving this rock and modifying the surface on very short timescales for a geologist of maybe 100 to 1,000 years. And we think often when we think about the way that water affects the surface of our planet, we think about this water cycle where we have evaporation from the oceans and precipitation onto the land and then erosion. But this is actually only a portion of what's going on our planet on the long time scale. And what we see at the surface is actually only part of the story. And the surface water cycle, it operates on these short timescales, but on long timescales, water is interacting with the entire interior of our planet as well. If you were here for Chris's opening remarks in the morning, he showed the size of the Earth's water relative to the size of the planet as a little blue droplet on the surface of the planet. And what he was showing there was the amount of water that we have at the surface. But in fact, we know that there is about as much water locked within the Earth's mantle as there is at the surface. So we, in fact, have 2 of those little bubbles, not just the one. And water is present in the Earth's mantle. It's locked inside of silicate minerals that we call nominally anhydrous minerals. So it's not a hydrated silicate, but is present sort of dissolved in the sort of interstitial spaces of these minerals. And it exists in the upper mantle, and the way it gets into the Earth's interior is by reacting with oceanic crust. And during plate tectonics, what happens is oceanic crust actually sinks beneath continents, and it subducts into the mantle, and it transports water into the interior of the planet. And so this is how we might actually lose some of our surface water into the interior of the planet. Now, once it's in the interior, water actually has a really strong influence on the material properties of the silicates, and it can enhance melting and viscosity, as I'll discuss in a moment. But it will get transported from the interior of the planet back to the surface through melting and volcanism. And that happens at regions like arc volcanoes, like the Japan Islands, or it can happen at places like mid-ocean ridges that are producing ocean crust in the middle of our oceans. And so this exchange of water between the interior and the surface, it affects the long-term habitability of the surface of the planet, and it might impact how long biology can last on a planet and when it can actually start. So that water is affecting the properties of the interior of the planet, again, as I mentioned. So it changes the melting temperature of rocks to the point where it actually helps us get water back out of the interior of the planet. On this figure, I'm showing that a rock that doesn't contain any water at all has a melting curve as we go down into the interior of the planet, shown by this blue line. And if we add a lot of water into that rock and saturate it, the melting temperature at those high pressures actually drops by almost 800 degrees. So this is a substantial effect that water is having on the rheology of the planet. Water is also affecting the viscosity of the planet. This is the property that determines how quickly a material can flow, like water versus honey. Honey has a high viscosity, water has a very low viscosity. You might not think that rocks flow, but the mantle of the Earth does convect, and it has a viscosity. It's quite large compared to honey or water. But when you add water into it, it actually lowers the viscosity of the interior. And so it increases the rate of mantle convection. It increases the rate of plate tectonics and subduction. And so it modifies how water is being transported in and out of the interior of the planet. And so we can model how this happens. And in fact, what we know is that many of the planets that we have observed in the habitable zones of other stars that we think might be habitable are actually a lot larger than the Earth. They're what we call super Earth planets. And so this process, we can model it for the Earth, and we know how the history of water on the surface of the Earth might look, but we wanted to know how does this operate on these larger planets. And so what happens is there's this temperature viscosity feedback, where as we add water into the mantle, through regassing or ingassing, it modifies the viscosity of the mantle, which causes the viscosity to drop, and that will allow the mantle convection rate to increase. That lets us put more heat out, and that causes the temperature of our interior to drop. And that then modifies the viscosity, which causes the viscosity to increase, slows convection, and allows water to build back up in the interior. So there's this feedback loop with water modifying the internal properties of the planet. And if we look at how this works for planets that are the size of the Earth or larger, we can look at the history, predict the history of water on the surface of these planets over the course of their lifetime. So here we're showing the history of water on the surface of a planet. This is just the mass of a planet relative to our surface water. So Earth has one ocean mass on the surface at the present day. And we're looking how water on the surface evolves over geologic time, starting from the time of that planet's formation. And we can see that we're showing this for different planet masses up to 5 times the Earth's mass. And we can see that it depends on the planet's size. And we just convert this here into a surface area fraction to look at how much of the surface of these planets should be covered by water. And we could see that for the larger planets, in fact, they have very little water on their surface right at the beginning of their lifetime. In fact, it takes almost 1 billion years, maybe 2 billion years, for oceans to start being released from the interior of the planet and forming a substantial reservoir on the surface. And so we have delayed ocean formation on some of these large rocky planets. And so that might impact both the origins of life and then the long-term stability of life. We can see that once water is established on the surface, it increases and becomes an increasing surface area coverage of that planet. With smaller planets, there might be some planets out there that Earth size are smaller. They in fact start gradually losing water to the interior of their planets. This is for a planet the size of Earth, but as we go to smaller planets, they may actually lose all of their water to the interior of their planet over the course of their habitable lifetime. And so this impacts the kinds of planets that we might want to look for when we're looking for life on exoplanets. Do we look for larger planets or older planets? If we're looking at a planet like the Earth, we might want to look at a younger planet. If we're looking at a planet larger than the Earth, we want to look for older planets to see established life. Now, going back to the habitable zone, and talking about how that habitable zone varies with time, we've talked about how the geology influences the habitability of the surface. But the evolution of the star's luminosity also influences not just the habitability, but whether a planet can in fact retain water on its surface and what happens to that water. So I'm going to draw your attention down to this planet down here, Proxima Centauri b. Proxima Centauri orbits a star about 1/10 of the size of our sun. And as you can see from this little movie, Proxima Centauri is actually interior to its habitable zone in its early history. That means that it is too hot to have liquid water on its surface for that first period. And many planets that we see today in the habitable zones of stars, these very small stars, likely went through a period like this where they were too hot to have liquid water on their surface. And during this time, these planets may exist in what we call the runaway greenhouse state. And this can potentially cause these planets to lose a large fraction of their water. I just want to go over what the runaway greenhouse state is. So a planet in radiative equilibrium should be emitting as much radiation out into space as it is receiving from its host star in order to maintain a stable temperature. And when it's at equilibrium, those fluxes should be balanced. A planet with a lot of water on the surface, if it's receiving, will put out sort of a characteristic outgoing radiation, depending how much water is present in the atmosphere, because water is, in fact, a very strong greenhouse gas. It has very strong absorption bands in the infrared where a planet's thermal energy would be emitted. And so it can trap heat at the surface of the planet. So as the amount of water vapor in a planet's atmosphere increases, its surface temperature increases. This figure over here on the right is showing us how much the surface temperature of the planet increases as we increase the water in the planet. So this is showing outgoing radiation. And so we can see what the surface temperature of a planet with a mostly water vapor atmosphere would look like for different absorb shortwave radiations, assuming that they're in equilibrium. So if we are receiving less than the so-called runaway greenhouse threshold, the intersection of this line with this outgoing long wave radiation tells us the surface temperature, and this is a happy surface temperature where water is stable as a liquid at the surface, and our surface temperature is nice and habitable. Once we get above this boundary, though, this is what we call the runaway greenhouse threshold, and this is where water becomes optically thick in the atmosphere, and the atmosphere can't emit enough radiation to space to cool itself. And so what happens is if we're getting more radiation from our sun than this threshold, then our surface temperature starts to run away. So we have to look for the intersection if we're receiving 10 times the runaway greenhouse threshold with one of these lines out here. And we can see that if we have 10 times the runaway greenhouse flux and we have the equivalent of 100 bars of water, our surface temperature gets up to 2,500 Kelvin. That is hot enough to melt all the rocks at the surface of that planet. And so when a planet is in this runaway greenhouse threshold, depending on the amount of water it has on its surface, it might be in what we call a magma ocean phase. And so here we've just calculated for some of the small planet population how much water it would take to melt their surfaces. These planets are primarily all interior to their habitable zones, so these are not habitable planets, but we can see that it doesn't really take very much water at all to melt their surface. For reference, the amount of water that the Earth's surface has is shown by this dashed line up here, and we are plotting planets here based on how much radiation they're receiving from their stars. We have a couple of planets highlighted here that really only take up to 1 bar of water vapor in order to melt their surfaces. For reference, that's the total atmospheric pressure of the Earth, so very tiny fraction of the amount of water that Earth has on its surface. Now we can model how this will go for these small planets around these small stars and see how that impacts their total water abundance and their long-term habitability by modeling this magma ocean process. So we model the planet as a liquid ball of silicate rock. So this is a molten planet. And what happens here is that these small stars, because they're so bright, they're also putting out a lot of really damaging high energy radiation that heats the top of the planet's atmosphere. It photolyzes the water that's in that atmosphere into hydrogen and oxygen atoms and drives escape from the atmosphere, predominantly of the hydrogen, because it's a very light element. And some oxygen can remain on the planet, and it will interact with the surface of the planet. But in this process, we're losing our water abundance that we need for habitability, and we're also generating oxygen. So this is just a description of how that process works. So we have water is being photolyzed in the atmosphere and producing these hydrogen and oxygen atoms, and some of that hydrogen escapes and some of that oxygen remains on the planet and reacts actually with the interior of the planet. And so in order to understand how much oxygen builds up in the atmosphere, we have to take into account reaction with the surface. But the remaining oxygen, it builds up as a false biosignature. Now, oxygen on the Earth is produced almost entirely by photosynthesis, by life. And so for astronomers looking for signatures of life around other planets, they want to know what they can look for in the atmospheres of these planets that would be the signature of life. And oxygen has been a strong candidate because that's what we have in our own atmosphere. But here we're showing that oxygen actually is being produced just by water vapor. And so not only are these planets desiccated, they've lost their water, they've now built up this false biosignature as well. Here we're showing some of the calculations where we've taken a planet that has the same amount of water as the Earth and allowed it to evolve through this magma ocean phase, and we predict how much oxygen builds up in its atmosphere. So here yellow is essentially we have lost all of the water vapor, all of the hydrogen from our water vapor, and built up huge amounts of oxygen in the atmosphere. So this yellow color represents to 200 to 300 times more oxygen in the atmospheres of these planets than exists in the Earth's atmosphere. And this is dependent on the chemistry of that mantle, because that oxygen can be taken out of the atmosphere and sequestered in the interior of the planet. But for a planet around a small star, we can see that if we have a wide range of initial water abundances, we can build up some of these massive oxygen atmospheres. Now we've looked through these models to see what these models are the most sensitive to, and we find less oxygen buildup in more massive planets. So super Earths will be less prone to this false biosignature, and it's also sensitive to some other planet parameters, but also sensitive to the stellar host star. So these are problems for planets around small stars like M dwarfs, but less of a problem for larger planets. And so this might guide where we try to look for signatures of life on other planets when we can probe the atmospheres of these small planets with future telescopes. So just to sum up, I've talked a little bit about some of the ways that water modifies the habitability of a planet on the long term, and how the actual geology of the planet also controls the water abundance on the surface. Oceans are forming later on larger planets and subducted away earlier on smaller planets. And so this will govern where life might be most stable and most happy on these planets that we're finding around other stars. And water can also produce this false biosignature that we have to be careful for when we go to try to find life on other planets. And so this should guide our observations in the future in trying to understand where we want to find life on other planets, but we have to be careful where we look. So I'll finish there, and thank you, and take your questions.
Thank you, Laura. Thank you. That was a fantastic education for our audience. And our audience is not filled with biologists, but I'm pretty sure it's not filled with astronomers either. And so the biologists probably still have some questions for you. And I'll just, because we're going to go into the group discussion very soon, I'm just going to ask you kind of 1.5 questions. So my question is, if I wanted to try to sum up your talk, I would have to say that what you're doing is trying to make the best kind of estimates and calculations that you possibly can for not just where and what kind of planet might have water, but how long that water would last, right? And so, yeah.
Exactly, right? Exactly. Okay. Because we want a planet that has water present when conditions are right for the origins of life, but we also want a planet that allows for long-term evolution of that life.
Right. And so it's sort of doubly complicated because, we read all these super simplified articles in the popular media about habitable planets. And that assumes that, first of all, that water is key to life, which we don't even know if that's absolutely true on other planets. We can discuss that later. And then it also assumes that we want the conditions to be sort of like they are on Earth. And so that's what the sort of zone, the distance from the star means, right? And then nobody ever talks about what you were just talking about a lot, which is for what period of time. When we talk about the Drake equation, which some people may know is used to estimate the number of habitable planets, and usually the limiting factor is when a civilization destroys itself. That's the length of time that people are interested in. But there's a probably longer length of time where there's viable water on the surface of the planet, and that's a lot of what you were talking about. And so I know that you and I are both astrophysicists, so I understand what you're talking about. But I know even that the field that you work in is not that gigantically populated compared to all these other people working on exoplanets. So, do we know a lot about this? Is it you telling us? How much do we really know about kind of how long water is likely to last on various planets?
That's a great question. There are a lot of people working on things like atmospheric escape, but understanding the connection between the atmospheres and the interiors over the long time period is not something that people have really gotten into very much for exoplanets yet, although people are getting there. But for the solar system planets, this is something that people have been working on for a long time. Earth is obviously our only actual example of a planet where water is currently present on the surface. But we definitely have evidence that water was present on the surface of Mars for much of its early history. And so understanding how Mars has lost water over its lifetime is important in constraining these kinds of habitable lifetimes for planets as well. And even Venus, although Venus we think of today as being much too hot to be habitable, there's arguments nowadays that, in fact, Venus could have been habitable for the first billion years of its lifetime. We think that Venus actually started off with water. The question is over what timescales Venus lost water. And some models, like mine, would predict it lost it on very short timescales and never had a habitable period. And other models suggest, in fact, that it could have been habitable for a much longer period. So we can try to test these kinds of models even within our own solar system.
That's perfect. You just anticipated my next half question, so I'm going to cede that to Chris, and just say that there's a lot of questions here that people have asked that have to do with observing water on other planets. And so let's see if we can come back to that in the breakout rooms after or in the bigger discussion. But right now, I'll just cede the floor to Chris for a minute. And then after Chris's question, we'll start the group discussion with everybody. So hopefully everybody is ready for that. Go ahead, Chris. Thank you.
Yeah, thanks, Laura, for that great talk. You know, I wanted to be Neil Armstrong when I was young, and I was looking out to the stars, and that's why I get on so well with Alyssa. Yes.
Yeah, and I wanted to be Jacques Cousteau, let's not forget. Right.
But yeah, I was very interested with what you were talking about with concerning subduction, and you know that you can lose water from the surface, either going into a planet or being lost. And so concerning the water that maybe gets subducted inside a planet, I guess there is a potential that will hold life, right? We will miss it because we can't see the water on the surface. We can't detect it spectrally, presumably. And I think more and more evidence is emerging that there is a lot of life inside our planet, right? And I wonder, yeah, how
Right.
that may be another place where life could be harboring inside our universe.
Right, exactly. There is definitely life found within these subducting slabs as they're going into the interior of the planet. In fact, as these subducting slabs are going into the interior, because there is so much water there is actually, it reduces the melting temperature. And so we get a lot of actual melting right at the subduction zone. That's why we have this ring of fire around the Pacific. In fact, the arc volcanoes like the Japan Islands are produced by this voluminous melt that is produced by water going into the mantle there. And so that might not be the best conditions for life, but we know that there are many more habitable environments that probably exist on planets than we can observe remotely on exoplanets through biology. In fact, we think there's a huge diversity of water abundances that planets could have. They could have a tenth of the amount of water that the Earth has, or they could have 100 to 1,000 times the amount of water that the Earth has. If they have that large amount of water, we may actually have mantles of high pressure ice actually forming above our silicate mantles and an ocean above that ice. And so that would fundamentally change all of our ideas about habitable environments on that kind of planet as well.
Excellent. Wow. Okay. I have like 1,000 questions.